Hey guys, we're finishing up 12.2 today, transformations to achieve linearity, but we're focusing on exponential models today. And if you remember, exponential models are in the form y is equal to a times b to the x power. And if your b is greater than 1, it's growth. And if it's less than 1, it's decay. And these are just some examples you may have seen or you may recall from the past. Now, how are we going to linearize a relationship that follows an exponential model? It's very similar to what we did with the power models, but we're only going to take the log or the ln of the response variable, so only for the y. So this is a situation where we have years, 2004, 2005, for example, and the fees associated with that year for the University of Arizona. And we are going to start by saying that X is going to represent the number of years since 2000. So 2004 will be an X of 4. You don't have to do it this way. You can actually input 2004, 2005, 2006. It will give you a different model, but it will give you the same predictions. The only difference is if you're using years since 2000 and you're using numbers like 4, 5, 6, then your X's when you're making predictions would be 4, 5, 6, that kind of thing. Whereas if you're using the years 2004, 2005, you'd have to make predictions with those same values. So just know that you can do it either way, but just be clear about what you're doing when you set it up. So we want to look at this relationship and see if it looks linear. So I'm going to go to my calculator and we're going to take a quick look at that. I already have my data entered in list 1 and list 2, and I want to do a scatter plot of list 1 versus list 2. So let's make sure we have everything set up. And that is not what I meant to do. So let me go back to my graph and list 1 and list 2. And list 2, and then let me make sure I don't have anything in here and I have an old regression there. So zoom 9. And what I see here is a positive relationship. It's curved. It's somewhat strong, but there appears to be maybe an outlier here. You would expect that to be a little bit higher to follow that overall pattern. But overall, it's a somewhat strong relationship. So let's go ahead and document that. Okay, so here is the scatter plot, and of course you want to make sure to put your labels for your axes. So I have years since 2000, and then I have fees. And then of course to analyze this, the relationship between years since 2000 and fees is positive, fairly strong, and has a curve pattern. There's one data point that does not quite fit the pattern as well, 2009, 2010. So maybe something happened in that year. They didn't raise their fees as they had been raising them, or maybe there was an unusually high jump the next year. Just really not sure, but that's what I'm seeing in the data. Okay, we're going to actually run a regression, and we want to go ahead and take the natural log of our y. Now, it says on your handout to do the natural log. We're going to do log, and there's a reason. I want to show you how to basically make your prediction using log, because last time we did the natural log. So I'm going to create a new variable, and I'm going to take the log of list 2. So I'm taking the log of my response variable. Now when I run the regression, I want to do X, which is our year since 2000, versus log of our fees. So I'm going to run that regression. Option 8, and I'm going to do list 1 versus list 3. And I'm going to store the regression, vars, y vars, and I'm ready to run this. Okay, and here's my regression output. So again, you want to write down your y-intercept, your slope, your r-square, and your r, because you're going to need these to make sure this is the appropriate model. You're going to need your r-square and your r. Okay, so let's take a quick look at what this is going to look like. And I haven't looked at the scatter plots. I need to do that anyway. So I want to look at list 3 versus list 4 here. I'm sorry, list 1 versus list 3. So I need list 3 here. So I have my year since 2000 versus my log of my fees. So zoom 9, and I ran the regression on that same data, and it fits it pretty nicely. So it goes through, you can see that there's pretty equal scatter above the regression line and below it. Looks pretty good. So let's go ahead and analyze this regression. And so basically I ran the regression using list 3 with log of fees, and that's what the model looked like. Again, you want to put your labels on. So this is my scatter plot of my x versus my log of y with the regression line on top. This is a regression output itself, everything that you want to write down. And then I need to do my residual plot. So I will show you how to do that real quick on the calculator, just reminding you. So I'm going to go into my plots, and I want my x's, but I want them with my residuals. So I'm going to go in and use second list, which will turn on that feature I can go and grab my residuals. Now remember, you have to run your regression before you can do this. And I'm going to get rid of this regression line and then zoom 9. So this will be a residual plot where I have my x's. So all of these are my x's, so I can go along and see what my x's are and see the associated residuals. So that's what I want to create a scatter plot of. Okay, so here's where we were. So make sure to put your labels on. Now what I see in the residual plot, I don't really see a distinct pattern, and it's pretty scattered above and below. I have a few more observations above, but overall it looks okay. And especially since the relationship does appear to be linear here once the data has been linearized, and then I have my R squared and my R, which are very strong, indicating very strong relationships. So let's summarize what we're seeing here. The scatter plot of years since 2000 and the log of fees is a strong positive linear relationship with no apparent outliers. The resulting model is log of fees will equal to the y-intercept 1.30505 plus the slope 0.144248 times years since 2000. Now you remember last time we had to take the log or natural log before we actually use the model. This time we don't. We're not actually using a transformed x. We're using our actual x values. And for each additional year past 2000, the predicted log of fees will increase by 0.144248. So when we interpret our slope, we have to make sure we understand the slope is going to basically impact the predicted log of fees, not the predicted fees. So you have to take that into account. And the residual plot shows no obvious patterns. However, I still do see this possible residual here. So you want to comment on that as well. Now, I want us to run the power model, and it's because we don't really know which form this is. We don't know if it's exponential or if it's power. So you're going to have to do this comparison quite a bit. So let me just show you how you're going to do this on the calculator. So I'm going to go ahead and take the, I think I use log, so we'll use log here, log of list 1. And then I want log of list 2. So log of list 2. So what I have is the log of my year since 2000 and the log of my fees. And if a power model is more appropriate, when I run the regression of list 3 versus list 4, I will get a stronger model. So let's go ahead and do that. And again, I want to use log of each. So the log of my year since 2000 and the log of my fees. And bars, y bars, store my equation again, because I'm going to look at all my graphs in just a second. Okay, so write down your R squared and your R in this model as well, and we'll compare in just a second. But let's look at the scatter plot. And so I'm going to do list 3 versus list 4. So this is just to see what the linear relationship is between the log. Now, to me, this looks a tad bit more curved than the other linearized data did, but it is more linear than the original data. So now let's look at the residual plot. So remember, the only thing you really have to change here is you want to change your y variable to your residuals. So it's going to be option 8 there. So I want the log of my x's versus residuals. I'm going to delete that regression line, zoom 9. Okay, so I also see a little bit more of a pattern here as well, meaning that this may not be as the best way to linearize this data. So let's go back and basically finish documenting this. So we have our power model where list 3 is log of years since 2000. List 4 is going to be log of fees. So I'm just showing you here how to do it in the tables. And then there is my scatter plot with a regression line on top. And then I have my actual model and my regression, my linear regression, and the R squared and R, which are very important when we're doing this analysis. And then here's my residual plot. So the scatter plot of log of years since 2000 and the log of fees is a fairly strong positive linear relationship with no apparent outliers. And the resulting model is, and it gives you there, we have log of fees is equal to the y-intercept plus the slope times log of years. And for each increase in log of years since 2000, the predicted log of fees increases by the slope. And the residual plot has more pattern than the last model. So I'm thinking that this may not be quite as good a fit for the data. So the exponential model is better because here I'm actually comparing the R squared and the R to the other model. So the exponential model, which is the first one that we ran, where we only took the log of y, appeared to give us a stronger model. So I think it is better, it does a better job at linearizing the data. So both are higher than the statistics for the power model. Therefore, we can conclude that roughly 96% of the variation in log of fees can be explained by the least squares regression model relating years since 2000 to log of fees. So remember, this is not linear between years and fees. It's linear between years since 2000 and log of fees. Okay, so here's our exponential model, and I wrote it all out. I just want you to understand how you're going to actually make predictions. So you write your model out just like you always do. And we have here, cannot get it to, so I have here the year since 2000, and that will be my input. And if I'm making a prediction for 2012, I will use 12 as my X, as my input. I input it into the model, and the log of fees is going to be 3.036026. So the reason I chose this is to remind you that the common log has an understood base of 10. So 10 to this power will equal to your fees. So I get 1086.49. Now, I think Pardee also said, is this going to be a good prediction? And is it too high, too low, or just about right? Well, we are extrapolating because our data was from 2004 to 2011. So we're going beyond that given data set. So it is called extrapolation, and it's hard to say if the model will continue to make good predictions outside the original data. However, it's only 1 year past the last observation, so we can be somewhat confident that it is accurate. So we think we'll see that same pattern continuing, but you can't ever be certain because it is extrapolation. Okay, you have an example M&Ms to do, and what I want you to do for the M&M example is I want you to basically determine if the given relationship is linear. If it's not, try both transformations. Try taking the log of both x and the log of y, and then also just take x versus the log of y and see which model gives you a better result.